Recall that an autotransformer is essentially a single winding transformer with a portion of the winding common to both the supply and the load side. In contrast to a two-winding transformer, it cannot provide isolation between the high voltage and low voltage side. Here, VA is transferred from one side to the other not only by magnetic coupling, but also by electrical conduction. Autotransformers are cheaper than a similarly rated two-winding transformer when the voltage transformation ratio is close to unity. A single-phase two-winding transformer, though, can be suitably connected to perform like an autotransformer. In this example, a 5 kVA 100 volt to 200 volt 50 Hz single-phase two-winding transformer is to be used to step up the voltage from 200 volts to 300 volts by connecting it like an autotransformer. We are to calculate the maximum kVA that can be handled by the transformer without overloading any of the high voltage or low voltage coils, and how much of this kVA is transferred magnetically and how much is transferred by electrical conduction. Connecting this transformer to simulate an autotransformer, we will move the 100 volt windings like this, connecting its unspotted side of the coil to the spot side of the 200 volt coil, making the voltages additive. I am going to redraw this arrangement to schematically look like this. When connecting a two-winding transformer as an autotransformer, it is essential to remember that the dot markings or polarities of the two coils are additive, meaning that the coils are now in series connected. Since the input voltage here is 200 volts, supply must be connected across the 200 volt terminals. The induced voltage in the low voltage side in turn gets fixed to 100 volts, but we require 300 volts as an output, so the 100 volt coil is to be connected in additive series with the 200 volt coil. Here the idea is not to exceed the voltage and current rating of the coils of the two-winding transformer. Now for the transformer having a rating of 5 kVA at a voltage ratio of 200 to 100 volts at 50 Hertz, we have the rated voltage of the high voltage coil is 200 volts. The rated voltage of the low voltage coil is 100 volts. The turns ratio is 200 to 100 or 2. The rated current of the high voltage coil is 5,000 divided by 200, which equals 25 amps. And the rated current of the low voltage coil is 5,000 divided by 100, which is equal to 50 amps. Since the load is in series with the low voltage coil, so the load current is the same as the current flowing through the low voltage coil. Thus, the maximum of 50 amps can be drawn by the load, otherwise we are overloading the coils of the transformer. The output kVA is equal to 300 times 50 VA, or 15 kVA, and the input kVA, of course, is the output equals the output kVA, which is also equal to 15 kVA. The current drawn from the supply, which is the input of 15 kVA divided by 200 volts, and that is equal to 15,000 over 200, which is equal to 75 amps. Now the question is, how much current is flowing in the high voltage coil, and in which direction is it flowing? We just observed that the load is in series with the low voltage coil. So the load current is the same as the current flowing through the low voltage coil, which is the output 15 kVA. And if we divide that by 300 volts, that gives us 50 amps. Applying Kirchhoff's current law at the junction between the upper and lower coils, we get the current through the high voltage coil is equal to 75 minus 50, or 25 amps. The direction of the current is obviously from the top to the bottom. No matter whether the two-winding transformer is used as a two-winding transformer or as an auto transformer, MMF must be balanced in the coils. If the current comes out through the dot terminal of the low voltage coil, current must flow in through the dot of the high voltage coil. It is important to note that as a two-winding transformer, kVA handling capacity is 5 kVA, the rating of the transformer. However, the same transformer, when connected as an auto transformer, kVA handling capacity becomes 15 kVA without overloading any of the coils. Ready to go beyond just solving problems? If you've been following my daily post and enjoying the sample problems, you're going to love this. All of these problem sets and more are now available, or soon will be, on my official course site, my stand store for electrical training. Just go to the web address that you see at the bottom of this slide, https://stand.store/GVB. In recent years, the reality of climate change has become impossible to ignore. Severe weather events are growing more frequent and more intense. For homeowners, this means that utility power outages are no longer inconveniences. They can last for hours, days, or in extreme cases, even longer. The question is no longer if, but when. You'll need a solution to keep your homes powered and your family safe. Now is the time to prepare and ensure that you're not left in the dark when the next storm hits. Here are some trusted resources to help you prevent power outages at home. 𝐃𝐈𝐒𝐂𝐋𝐀 Canada at this web address, 𝐃𝐈𝐒 USA at this web address, BlueEddy Canada at this web address, BlueEddy USA at this web address, and BlueEddy Australia at this web address. And finally, you can get EcoFlow at this web address.